According to National Electrical Code Section 310.15b3, if the ampacity of the feeder conductors is sized for the sum of the overcurrent protective device ratings of all the branch circuits supplied, then the feeder conductors do not need to be protected against overcurrent. In this scenario, the feeder conductors are sized for 250 amps, which is the rating of the overcurrent protective device, specifically the fuse disconnect. Therefore, the feeder conductors do not need to be protected against overcurrent again. To further elaborate on this concept, let's break down the key components. Firstly, we have the distribution blocks. These are essentially convenient termination points for distributing power to multiple circuits. They allow for organized and efficient wiring within a control panel. The initial power feed to the first distribution block is provided by a 250 kc mil wire, protected by a 250 amp fuse in a separate disconnect enclosure. This establishes the primary overcurrent protection for the entire downstream circuit. The first distribution block then has two sets of output terminals. One set is used to feed the loads directly connected to that block. The second set of terminals is used to feed the second distribution block. The wire size used for this connection is number 2/0. The ampacity of this number 2/0 wire must be sufficient to carry the calculated load of the second distribution block. The calculation involves determining the total amp draw of all the outputs connected to the second distribution block and multiplying that value by 125% or 1.25. This 125% factor is often required by the NEC to account for continuous loads. A continuous load is defined as a load that operates for 3 hours or more at a time. By multiplying the total amp draw by 1.25, we ensure that the wire is adequately sized to handle the sustained current without overheating. The crucial point is that the 250 amp fuse provides the overcurrent protection for the entire circuit, including the conductors feeding the second distribution block. The NEC permits this arrangement under specific conditions primarily outlined in Section 310.15b3. The key requirement is that the ampacity of the feeder conductors, in this case the 250 kc mil wire and the number 2/0 wire, is sufficient for the applied load and that the overcurrent protection is adequately sized. In this situation, because the number 2/0 wire's ampacity is chosen to carry the calculated load of the second distribution block plus the 125% continuous load factor, it is acceptable. The question then arises, why not use a smaller fuse to protect the number 2/0 wire directly? The answer lies in the overall system design and the specific requirements of the connected loads. The 250 amp fuse is likely chosen to protect the entire system, including all the loads connected to both distribution blocks. If a smaller fuse were used for the number 2/0 wire, it could potentially trip prematurely, interrupting power to the second distribution block even if the total current draw is within the limits of the 250 kc mil wire. This is permissible because the loads attached to the second distribution block are accounted for in the overall load calculation of the panel, and the 250 amp overcurrent device is rated to protect the entire circuit including the smaller downstream conductors. To reiterate, the NEC allows for this type of arrangement when the feeder conductors are sized appropriately for the load they carry, and the overcurrent protection is adequate for the entire system. However, it is crucial to carefully calculate the load, select the appropriate wire sizes, and ensure that all connections are made properly. Incorrect wiring or undersized conductors can lead to overheating, insulation damage, and potentially electrical fires. Let's consider a hypothetical example to illustrate this concept further. Suppose the total amp draw of the outputs connected to the second distribution block is 80 amps. Multiplying this by 1.25 gives us 100 amps. Therefore, the number 2/0 wire must have an ampacity of at least 100 amps. According to the NEC ampacity tables, number 2/0 copper wire typically has an ampacity of around 175 amps, depending on the insulation type and installation conditions. Since 175 amps is greater than the required 100 amps, the number 2/0 wire is adequately sized for the load. It is important to consult the NEC ampacity tables and consider directing factors for ambient temperature and conduit fill when determining the appropriate wire size. Directing factors are adjustments to the ampacity of a conductor based on environmental conditions. For example, if the ambient temperature is very high, the ampacity of the conductor must be derated to prevent overheating. Similarly, if multiple conductors are installed in the same conduit, their ampacity must be derated to account for the increased heat generated. In summary, the NEC permits the use of a single overcurrent protective device to protect multiple conductors of different sizes, provided that the conductors are sized appropriately for the load they carry, and the overcurrent protection is adequate for the entire system. It is essential to carefully calculate the load, select the appropriate wire sizes, and consider all relevant directing factors to ensure a safe and reliable electrical installation. Remember to always consult the latest edition of the NEC and follow all applicable local codes and regulations. Electrical work can be dangerous, so it is important to take all necessary precautions and work with qualified personnel. To provide even further clarity, let's examine some additional aspects of this wiring configuration. Firstly, the distribution blocks themselves must be properly rated for the voltage and current they will be carrying. The manufacturer's specifications should be consulted to ensure that the distribution blocks are suitable for the intended application. Secondly, all connections must be made securely and with the appropriate torque. Loose connections can create resistance, leading to overheating and potentially electrical fires. Torque wrenches should be used to tighten connections to the manufacturer's specified torque values. Thirdly, the wiring must be properly supported and protected from physical damage. Cables should be secured with cable ties or clamps at regular intervals to prevent them from sagging or rubbing against sharp edges. Conduit or other protective measures should be used to protect wiring in areas where it is exposed to physical damage. Fourthly, the control panel itself must be properly grounded. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protective device and prevent electrical shock hazards. The grounding system should be installed in accordance with the NEC and all applicable local codes and regulations. Fifthly, it is important to label all wiring and components clearly and accurately. This makes it easier to troubleshoot problems and perform maintenance in the future. Wire markers and labels should be used to identify the function of each wire and component. Sixthly, a complete set of drawings and documentation should be maintained for the control panel. These drawings should show the wiring diagram, component layout, and all other relevant information. This documentation is essential for troubleshooting, maintenance, and future modifications to the control panel. Seventhly, regular inspections and maintenance should be performed on the control panel to ensure that it is operating safely and reliably. These inspections should include checking for loose connections, damaged wiring, and other potential problems. Any problems that are found should be corrected promptly. Eighthly, it is important to be aware of the potential hazards associated with working on electrical equipment. Electrical shock is a serious hazard that can cause injury or death. Always de-energize the equipment before working on it, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. Ninthly, it is essential to follow all safety procedures and guidelines when working on electrical equipment. These procedures are designed to protect you from electrical shock and other hazards. If you are not familiar with these procedures, seek training from a qualified instructor. Tenthly, always use the correct tools for the job. Using the wrong tools can damage the equipment and increase the risk of injury. Make sure that your tools are in good condition and properly insulated. To delve even deeper, let's address some common misconceptions about overcurrent protection. One common misconception is that the overcurrent protective device must always be sized to protect the smallest conductor in the circuit. While this is often the case, it is not always required, as we have seen in this example. The NEC allows for certain exceptions, such as when the larger overcurrent protective device is protecting the overall system and the smaller conductors are adequately sized for the load they carry. Another misconception is that the overcurrent protective device will always trip immediately when an overload occurs. In reality, overcurrent protected devices have inverse time characteristics, meaning that they will trip faster for higher overloads and slower for lower overloads. This allows for temporary overloads, such as motor starting currents, without tripping the overcurrent protective device. Another important consideration is the interrupting rating of the overcurrent protective device. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without failing. The interrupting rating must be high enough to handle the maximum fault current that is available at the point of installation. If the interrupting rating is too low, the overcurrent protective device could fail during a fault, potentially causing a fire or explosion. The available fault current can be calculated using engineering formulas or determined through a fault current study. A fault current study is a detailed analysis of the electrical system to determine the maximum fault current that is available at various points. This study is typically performed by a qualified electrical engineer. In addition to the overcurrent protective device, surge protection devices, or SPDs, may also be used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, or other events. SPD are designed to divert surge current away from sensitive equipment, preventing damage. SPD should be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. Another important aspect of electrical safety is arc flash protection. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault creates an arc of electricity. Arc flash can cause severe burns, blindness, and even death. Arc flash hazards can be reduced by using appropriate personal protective equipment, such as arc-rated clothing and face shields. Arc flash studies can also be performed to determine the arc flash hazard levels at various points in the electrical system. This information can be used to select the appropriate personal protective equipment and to develop safe work practices. To further enhance your understanding, let's explore the different types of overcurrent protective devices. Fuses are one type of overcurrent protective device. Fuses contain a fusible link that melts and opens the circuit when an overcurrent occurs. Fuses are available in a variety of sizes and types, with different current and time delay characteristics. Circuit breakers are another type of overcurrent protective device. Circuit breakers use a mechanical mechanism to trip and open the circuit when an overcurrent occurs. Circuit breakers can be reset after they have tripped, unlike fuses, which must be replaced. Circuit breakers are also available in a variety of sizes and types, with different current and time delay characteristics. Some circuit breakers also have ground fault protection, which protects against ground faults. A ground fault occurs when current flows from a live conductor to ground. Ground faults can be dangerous, as they can cause electrical shock hazards. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. GFCIs work by monitoring the current flowing in the hot and neutral conductors. If there is a difference of more than a few milliamperes between the two currents, the GFCI will trip and interrupt the circuit. This indicates that current is flowing to ground, which could be a shock hazard. In summary, understanding overcurrent protection is crucial for ensuring the safety and reliability of electrical systems. By following the NEC and all applicable codes and regulations, and by carefully selecting and installing overcurrent protective devices, you can help to prevent electrical fires, electrical shock hazards, and other potential problems. Also, keep in mind that this is not a substitute for consulting with a qualified professional. Electrical work is dangerous and should only be performed by those with the proper training and experience.